I've had a couple of people ask me, what does it mean exactly for a coefficient to be unbiased? So I wanted to remind you that back in chapter 4, we did have a econometric definition of what it means to be unbiased that we illustrated in the single variable case where we looked at the ordinary least squares estimator. And this is a nice way to review a key idea in econometrics. So you'll remember that our estimator of the slope coefficient beta 1 hat was given by this formula, the sum of yi minus y bar times xi minus x bar divided by the sum of xi minus x bar squared. And you saw this on your midterm where you calculated the slope coefficient by hand using this formula. And it's good now to go back and look at that midterm and see how you did it and be reminded of how you did it and why you did it this way, why this was the ordinary least squares estimator. But this estimator, beta 1 hat, with this formula, will be different for every sample. So every sample that we take, for every sample that we take, we'll get a different beta 1 hat. So we might want to ask, well, what's the expected value of beta 1 hat? And use this expectations operator. Suppose we took a whole bunch of different samples. What would be the expected value of beta 1 hat? Well, let's look at the expected value of beta 1 hat. So that's just the expected value of the term that is beta 1 hat. And remember, this is the expectations operator introduced in chapters 2 and 3. So the expectations operator, it's the sum of all outcomes times their probabilities. But we just use the capital letter E to summarize that. So E stands for the sum of every possible sample with, not every possible, all the samples that we have, with the probability of getting that sample. So it's the expected value then of doing these calculations on each sample, the expected value of beta 1 hat is what we have here. So we can do some more math with that. Inside, yi, so if we go back here, right, here's yi. If we look at that, well, yi by definition is beta 0 plus beta 1 xi plus ui. That's our population regression model. And y bar then is just the mean of that. So the mean of a set of terms is just the sum of the means of those terms. So that's the mean of beta 0 is just beta 0, the beta 1 times xi is just beta 1 x bar, and u bar is, sorry, the mean of u is just u bar. And remember, the mean of u by definition is equal to 0, so that's going to drop out. I'm being a little loose here with the math, right? So we're going to have then beta 1 xi minus beta 1 x bar plus ui times x minus x bar divided by the sum of x minus x bar squared. Now I have a common factor here. I have beta 1 times xi and beta 1 times xi bar, so I can have beta 1 times xi minus x bar here, and then multiplied by the other x minus x bar, and then I can take the ui multiplied by the x minus x bar and end up with this term. And they're both being divided by the sum of squares, deviations. Then I can take those two terms and separate them. You can go back and look and see what I've done. All I've done is separated out the terms. Now, the expected value of beta 1 is beta 1 is a number. It's the true population coefficient, so we can bring it outside of the expectations operator, and then these two cancel, so we just have beta 1 here, and then we take the expectations operator to this whole term, and we get the expected value of all of this. Now, one of the rules of expectations operators is the expectation of an expectation is the same thing, so we can put the expectations term in here on this ui, a little bit of rearranging here. But remember our assumption about the expected value of the error term. The expected value of the error term is conditional on the x size is that it's equal to 0. So this, our main assumption that the expected value of the error term conditional on the x's is equal to 0 means that the expected value of the coefficient, the expected value of beta 1 hat, is equal to the true population parameter. So OLS is unbiased in that sense. It's unbiased if the expected value of the error term, conditional on the xi's, is equal to 0. If this condition is not true, then this term here is not equal to 0, and this term is not equal to 0, so then the expected value of beta 1 hat is not equal to beta 1, and that's what we mean by saying the coefficient is biased.